Thank you so much for the introduction. So today I'm going to be talking about statistical guarantees for data-driven posterior tempering. This is joint work with my advisors, Marco and Cindy, also at Columbia. And so to kind of set up some, for some setup and to introduce notation. So we're all familiar with kind of the usual framework of posterior inference, where we have a set of observations and latent variables, and we, try to, compute or make inferences using the conditional distribution of the latent variables given the observed data. And so in this talk, we're going to be studying a variant of this procedure that's called the alpha posterior, or like the kind of power tempered, many names for this object. And what we're doing is we're taking the likelihood and we're raising it to a power and then kind of renormalizing this object so that it's a proper density. And in this talk more specifically, we're going to be focusing on this object when the alpha was somehow chosen in a data-driven way. And kind of one sub question of this is, how should we select the alpha in a data-driven way, and when we do so, how does that selected parameter behave? And then kind of the second question is what does that imply in turn for the resulting alpha hat posterior? What kind of statistical guarantees can we recover from selecting the alpha in a data-driven way? So before I go into our main results, I'll kind of introduce some motivation for this procedure in the first place. And so, the idea to decrease the influence of the likelihood in the calculation of the posterior is something that's appeared in a lot of procedures, things like density estimation and aggregation of estimators. But, in the past 10, 15 years, the specific alpha posterior object has been studied as a kind of more robust alternative to the standard posterior. And so a few examples of this are, Peter Grunwald's safe Bayes method in the case of misspecified linear regression, the Thorson posterior by Miller and Dunson, and then kind of recent work with my advisors Cindy and Marco that have kind of characterized rigorously some of the robustness properties that can be gained by using this alpha posterior. And kind of another motivation is that these posteriors are a special case of Gibbs posteriors, and the references I provided are not comprehensive. There's so much work in recent years on this, and you're going to hear a lot about these Gibbs posteriors at the workshop, so I wanted to highlight that as well. So in terms of statistical guarantees for these alpha posteriors, in high dimensional settings, we have results about concentration. We also have asymptotic results in semi-parametric settings. But in this talk, we're going to be focusing on asymptotic guarantees and second order behavior of these posteriors in like parametric low dimensional model settings. And I wanted to also highlight that I've included references at the bottom here that a lot of these conditions and results come from results about standard posteriors and Gibbs posteriors as well. So now we'll kind of dive into our first question. So how should we select alpha in a data-driven way? And before I do that, I'll kind of go and give like a rough overview of some of the methods that have been proposed. So, there's been, like some methods about, this work by Holmes and Walker on equalizing the information gained between the prior and the posterior. There's, in recent years, there's been a lot of work that's been more calibration based. And in this, in this talk, we're going to be focusing on methods that optimize for prediction or more cross-validation based. So we can think of the safe Bayesian method in this way, and then also some other recent work has touched on this as well that I'll dive into later. So and specifically we're going to look at this kind of simple example of Bayesian linear regression. So it's kind of well known that there's this sort of equivalence between Bayesian linear regression and ridge regression. So if we have a typical IID error regression model and we put a spherical prior on the coefficients, and if we set alpha in this particular way to be essentially inversely proportional to the regularization parameter lambda, then the resulting kind of alpha posterior is a Gaussian that's centered at the ridge regression estimator. And so kind of to make a couple remarks about this example and why we found it interesting. So first, there's kind of this, we do kind of know from like frequentist, like asymptotic theory that there are some regimes of this regularization parameter lambda that correspond with the, consistency and asymptotic normality of the ridge regression estimator. And so if you, kind of take these regimes and then convert them to the corresponding regimes of alpha based on the, definition of, like alpha is 1 over n lambda, then these kind of regimes also correspond with the regimes where the alpha posterior, so as in the this specific alpha posterior, is asymptotically normal, and then where the, alpha, the kind of the mean of that alpha posterior is root n consistent. So there's some sort of correspondence between this, ridge regression theory and then alpha posterior inference. And so, one of the contributions of our work is we sort of generalize these findings to alpha posteriors from, parametric rank families. The second kind of remark I wanted to make is about data-driven selection of alpha. So we looked at some kind of these like Bayesian cross-validation type methods for selecting this alpha parameter in the context of this ridge regression, and so this is the context in which I met Yem because we were working on kind of the similar things. And so we observed kind of, an interesting distribution of alpha hat. So I'm kind of thinking of a numerical experiment where we're, over many independent replications of the data, we're looking at, the distribution of the selected alpha values using some sort of Bayesian cross-validation. And so this is the distribution we observe when, the data set is, size 100 versus 1,000. And so we observe a couple of things. So first, we observed kind of this point mass where approximately half of the time, the selected alpha value is essentially alpha equals infinity. And then kind of the remaining sort of non-degenerate values belong to this vanishing regime. So we can kind of show numerically that the kind of values that I've circled here are decaying to 0, but they're decaying slower than 1 over n. And so we call this entire regime the mixed regime. So with some probability, the alpha is selected to be infinity, and with remaining probability, it belongs to the vanishing regime. And so this is something that was also, as I mentioned, observed by Jeremias's group, as well as it's been observed in also like frequentist holdout validation schemes in the context of ridge regression as well. So now I'll kind of, go in turn to, essentially characterize the behavior of the alpha posterior in these sort of two regimes, and then we draw some conclusions about its behavior in this mixed regime. So kind of before I go into our like theory results, I'll kind of introduce some more notation. So we specify a family of statistical models by cal fn, so some family that's indexed by a parameter theta. And we say that our model is misspecified if the true density of the observations does not belong to this specified family. And so what that in turn implies is that, or what we'll kind of consider here is that we'll consider convergence in terms of this true probability measure in a sense. We can define the maximum likelihood estimator as usual. And one thing to note here is that this MLE is going to be consistent for some theta star. So if our model is correctly specified, then this theta star would correspond to our true parameter. And if it's misspecified, then theta star corresponds to a pseudo true parameter, which essentially indexes the model in cal F that's closest to the true density in terms of KL divergence. And before I kind of introduce the results, I'm going to kind of display the types of conditions we're considering, because the actual conditions are a little dense to get through. But the types of results that we're going to be thinking about require 3 conditions. And when I say types of results, I mean like asymptotic normality types of results. So first, we need kind of a prior mass condition that says that the prior will put enough mass near the pseudo-true parameter, which will kind of guarantee that the posterior will be essentially consistent for this pseudo-true parameter. We need a local condition that essentially dictates that the log likelihood is going to be well behaved or approximately Gaussian near the pseudo-true parameter. And then finally, we need a tail condition that says kind of outside this local neighborhood, the behavior of the posterior is negligible in some sense, which kind of allows us to include that the local Gaussianity is what characterizes the posterior. And then we can kind of draw conclusions about, the distribution and its moments and things like that. So now we'll kind of present our main results in this vanishing regime. So our first result is an asymptotic normality result. So under some regularity conditions that I'll specify later, if we have that alpha hat belongs to this vanishing regime with high probability, then essentially what we will show is that the alpha hat posterior is close to this limiting Gaussian for sufficiently large n. And this limiting Gaussian is notably centered around the MLE, and it has kind of this asymptotic covariance that's related to the curvature of the misspecified log likelihood in some sense, and it's scaled by this 1 over alpha hat n times n. So this matches kind of previous results about alpha posteriors where the alpha is constant and doesn't depend on the data. And essentially, we're kind of corroborating the previous results that essentially say that the effect of tempering on the alpha on the resulting posterior is that it changes the effective sample size from n samples to alpha times n samples. To arrive at this result, we need a few conditions. So throughout, we'll kind of assume, usual regularity of the maximum likelihood estimator. We assume kind of a prior mass condition that simply dictates the priors, continuous and positive, the pseudo-true. We also need a local asymptotic normality condition that's kind of similar to the usual lambda. So we can achieve this kind of by plugging in alpha equals 1, and we can kind of recover the usual lambda assumption. And essentially, this is a third order Taylor expansion of the likelihood ratio. And then finally, we assume our tail condition is the posterior concentration assumption. Our next result is a result about moment consistency. So under an additional assumption that I'll detail later, we have the following result. So if we take the alpha posterior, we center it around, so I'll kind of talk through this notation. So we're going to center the alpha posterior around the pseudo-true, and we're going to scale it by, root alpha n, and then we're going to look at, the moments up to the moments, and we essentially get that, the moments converge to those of the limiting Gaussian. And to arrive at this result, we require kind of a finite moment assumption that's a bit stronger than posterior concentration. And so our last kind of result in this vanishing regime is a root n consistency result of the posterior mean. So this is a little stronger than the previous result in the sense that we're kind of getting a root n consistency result, even though we're just looking at the first moment. And so kind of the main takeaway to observe here is that essentially what this statement is saying is that the posterior mean and the MLE are, asymptotically equivalent, but only in a restriction of the vanishing regime. And kind of the reason that this is the case is, we essentially use a Laplace approximation argument to establish that the difference between these two objects is also of order, 1 over alpha times n. And so in a sense, we're kind of characterizing the effect of tempering on the bias of the posterior mean. And, that kind of explains this sort of restriction. And so this is kind of like, this is somewhat of a, an insight that we hadn't been able to observe before. To arrive at this result, we need kind of different conditions, but they still fall into the broad buckets that I described before. So now, we're dictating the prior is differentiable rather than simply continuous near theta. We're taking kind of another derivative of the log likelihood ratio. And we're also requiring an MLE kind of separation condition that, we can sort of see in the sense that it's a tail condition in the sense we consider neighborhoods sort of out. We consider, neighborhoods far from the maximum likelihood of good. Our kind of last result now is, characterizing what happens in the mixed regime. So I'm kind of detailing the situation before where, let's say that our alpha hat n mix is vanishing with some probability, and then in, infinity with remaining probability. And so what happens to the resulting alpha posterior? Well, the resulting alpha posterior is also kind of a mixture, with one component being a point mass at the MLE, which corresponds to alpha being infinity, and then with remaining kind of component being the sort of limiting normal from our first asymptotic normality result. So essentially, kind of by characterizing these regimes separately, we can combine them and then obtain a result in the mixed regime. So kind of to wrap up, we looked at alpha posteriors where the alpha depends, on the data in some potentially arbitrary way, and we characterized the behavior of the alpha posterior in the sort of novel regime for the alpha is, potentially either infinity or converging to 0 or vanishing. And so kind of some, future work that we're interested in is there's been some work kind of characterizing the robustness properties of variational approximations to alpha posteriors. And so we wonder, to what extent do these guarantees carry through to those approximations? We are also kind of interested in potentially other, posterior functionals and, perhaps some, so kind of this like prior differentiability kind of reduces how much we can do with our Laplace approximation. So any kind of non-differentiable function of theta, what can we say about root inconsistency or not? And then finally, do the kind of appealing robustness properties of alpha posteriors, do they carry over to certain high dimensional settings? So that's something that we'd be interested in looking into. And thank you so much for your time, and I'll take questions.
Thank you. Do we have any questions? Yes.
Thanks for the talk. I wanted to ask, I have always been wondering if it's alpha posteriors or power posteriors. Isn't the alpha and least polynomial distribution just like a scale parameter?
Yes, it's yeah, exactly.
So why do we fix it instead of also doing Bayesian inference on that? Or like, what's the idea of having like a fixed scale parameter and choosing?
So I guess, are you asking why we just don't do Bayesian inference on the alpha parameter?
Exactly, yeah.
Yeah, so this is something that like we tried and like other people have tried. I think there's like a few justifications for not doing it. One is kind of, I think there's like a philosophical type of idea that like beyond non-Gaussian cases, the alpha parameter doesn't have it's not as meaningful in the model specification, and so people don't believe that specifying a prior on it is like the right thing to do philosophically.
I think for exponential family it would still be
Yeah,
kind of
yeah.
right.
It carries through for exponential family. I think beyond that, it's like a little bit dicey, but it's more like a philosophical reason. Kind of another reason is that when you can try out examples and like so for example, I think you can put like some sort of like exponential or gamma prior on the alpha, and then look at the posterior, look at the the resulting like map estimator of alpha, and this alpha that you get is actually like it's of order 1/n. And I didn't talk about this, but this is sort of a case where we don't get an asymptotic normality result, like your posterior doesn't contract, and so one of the things is like what you get out of putting a prior on alpha isn't necessarily desirable in the sense that you don't get a posterior that contracts. So that's kind of another reason people don't like to do it. And then maybe like a third kind of reason is there's like a little bit of difference between the alpha. So I agree that the alpha kind of corresponds to like you can kind of either like there's like a trade-off between like the alpha and Gaussian regression and then like the prior variance and these type, there's like a trade-off there. I guess the difference with alpha posteriors is that the effect of the alpha stays asymptotically, whereas the Bernstein-von Mises theorem kind of tells you that the effect of the prior vanishes asymptotically. So that's kind of why like they're like slightly different things, even though I do agree that in the Gaussian case, you can kind of describe the trade-off very clearly.
Any other questions? Yes.
Thanks a lot. So one thing that I'm always wondering with these asymptotics for alpha posteriors, and I haven't been clever enough myself to come up with this, so probably the answer is no. But because most of the regularity conditions, relate to these like very nice regular models that we can study well. But I think practitioners, if you speak to them, they're most interested in raising things to like the likelihood to some power if they work on hierarchical models or the slightly more complicated Bayesian machines where it's convenient because you can just modify one component. Have you looked at, or do your assumptions apply to these settings? I assume no, but how difficult would it be to carry some of these assumptions over to these machines? Or is it essentially impossible?
I'll be honest that I haven't like personally looked at it myself. But I'm thinking of like there's like another work on kind of like establishing these types of guarantees. So there's like a guarantees for like sort of like variational approximations to posteriors in general. And so like there's like a specific paper I'm thinking about where they do apply, they have similar regularity conditions as we do, and they're able to kind of apply them to their examples. I'm assuming that as long as like at each level of the hierarchy, the model itself is smooth enough, it probably should be okay. But but like take with a grain of salt because I haven't.
I think if you think it should be relatively easy to do, it might be worth looking into because I don't think anyone has really done that. And I know that in that biostats community that uses these objects, I think hierarchical setting is very interesting to them.
Do we have any other questions? If not, then I think we'll all just go back upstairs for a coffee break. We'll be back downstairs at some point soon for some various conference. Thanks again.